I've been looking over the switching and routing syllabus, and the jump from layer 2 to layer 3 switching always feels a bit abstract. Beyond just adding routing, how do you view the practical shift in how data moves through the fabric of a campus network?
Think of it as moving from a neighborhood delivery service to a regional logistics hub. In Layer 2, we're just looking at MAC addresses to decide which door to knock on, but once you hit Layer 3, the switch actually starts inspecting the zip code or IP header to navigate across different subnets.
That makes sense, especially when you consider VLANs. If we use a Layer 2 switch, we're stuck in our own silos unless we use router on a stick. But a Layer 3 switch lets those VLANs talk to each other right at the hardware level, which significantly cuts down on latency, doesn't it?
Exactly, because you're avoiding that bottleneck of sending every inter-VLAN packet up a single physical link to a router. But even with that speed, we still have to deal with the chaos of loops, which is why the syllabus emphasizes spanning tree and its faster cousin, RSTP.
STP is interesting because it's basically the network's autoimmune system. It kills a link to save the whole body from a broadcast storm. However, relying on one link feels risky, which is probably why the exam focuses on link aggregation to combine bandwidth while maintaining redundancy.
Right, it's all about balancing efficiency and uptime. Moving to the routing section, I noticed a big emphasis on OSPF over RIPv2. In a medium-sized campus, OSPF's ability to divide the network into areas seems crucial for keeping the routing tables from becoming bloated and unmanageable.
OSPF is definitely the heavyweight there, especially with how it calculates the shortest path based on link cost, rather than just hop count like RIP does. But for the edge of the network, do you think static and floating routes are still the go-to for connecting to the ISP?
For sure, because you don't want to run a complex dynamic protocol with your provider. A simple default route does the trick. Then you use a floating static route with a higher administrative distance as a backup path that only wakes up if the primary link goes dark.
And then there's NAT and ACLs acting as the gatekeepers. It's funny how NAT started as a way to save IP addresses but became a de facto security layer, while ACLs give us that granular control to say the accounting VLAN can't talk to the guest Wi-Fi at the packet level.
It's a lot to juggle, but using tools like ENSP mentioned in the syllabus really helps visualize these mechanisms. It's one thing to read about an ARP broadcast, but seeing it fail in a simulation because of a misconfigured one-arm router really makes the theory stick.
Speaking of simulations, I've always found the transition from DHCP on a local switch to a centralized router pool a bit tricky. The syllabus mentions both interface and global pools. How do you decide which one to deploy in a real campus environment?
Interface pools are great for small, isolated setups because they are so quick to configure on a specific port. But for a medium-sized network, global pools are the way to go, because they give you a centralized bird's-eye view of your entire IP address management strategy.
That makes sense for management, but then we have to ensure the gateway is reliable. If that one router acting as the DHCP server or gateway goes down, the whole department is offline, which brings us to the importance of VRRP for gateway redundancy.
Exactly. VRRP is like having a stunt double for your router. The hosts think they are talking to one virtual IP, but behind the scenes, a backup router is ready to take over the MAC and IP duties in milliseconds if the master fails.
It's all about creating that illusion of a single, unbreakable path. I noticed the syllabus also touches on IPv6. Do you think we're finally reaching the point where students need to prioritize it over traditional NAT-based IPv4 setups?
We're in a hybrid era, so mastering both is mandatory. While NAT keeps IPv4 alive by masking private addresses, IPv6 simplifies the header and eliminates the need for NAT entirely, which actually restores the original end-to-end model of the Internet.
True, but until that transition is complete, we're still stuck writing complex ACLs to manage traffic. It's interesting how an ACL can be used for both security, blocking specific ports, and for identifying traffic that needs to be translated by NAT.
That dual purpose is key. You're using the same, matching, logic to either say, drop this packet, or this packet is allowed to go to the Internet. It really shows that switching and routing isn't just about moving data, but about intelligent traffic control.
I guess that's why the comprehensive training project at the end is so vital. You can't just understand OSPF or VLANs in a vacuum. You have to see how a loop in the spanning tree can actually break your routing protocols and disconnect your NAT gateway.
That's the aha moment for most students. Once you see the whole topology in ENSP and realize every configuration, from the duplex mode on a port to the OSPF area ID, is a gear in a much larger machine, you're finally thinking like a network engineer.
We've talked a lot about the logic, but I'm curious about the hardware side mentioned in the syllabus, specifically adding modules to routers. Does the physical port naming, like Gigabit Ethernet 0/0/1, actually matter when we're designing the topology?
It's critical for documentation and troubleshooting. Those numbers represent the slot and the port index. If you're trying to debug a trunk link in a dark data center, knowing exactly which physical lane is carrying your VLAN traffic saves hours of blind guessing.
That ties back to the memorization goal of consulting technical manuals. I've noticed that if the duplex modes don't match on a link, you might see the interface stay, bup, but the actual performance drops to a crawl because of constant packet collisions.
Exactly, a duplex mismatch is a classic, silent killer of network speed. It's why the syllabus pushes for understanding port speeds in auto-negotiation before even touching high-level routing protocols like OSPF.
Speaking of OSPF, how do you explain areas to someone who just wants everything to be in Area 0? Is there a practical limit to how big a single area can get before the CPU of a small router just gives up?
In a flat network, every time a link flaps, every router has to recalculate the entire map, which is exhausting. By using non-backbone areas, you're essentially telling the routers, only worry about your local neighborhood. I'll give you a summary for the rest of the world.
That's a great way to put it. It's the same reason we use route redistribution. Sometimes you have a legacy branch office running RIP and a main campus on OSPF, and you need a translator router to bridge those two different languages.
And that translator becomes a very sensitive point in the network. If you aren't careful with how you redistribute, you can accidentally create routing loops that circle between the two protocols forever, which is why metric manipulation is such a focus.
It feels like the whole course is a lesson in control versus connectivity. You want everything to talk, connectivity, but you use VLANs, ACLs, and areas to make sure they only talk when and where they are supposed to. Control.
Spot on. Whether it's the security of an ACL or the reliability of a VRRP group, you're building a system that is robust enough to handle failures without the end user ever realizing a cable was even pulled.
We've covered the logic and the hardware, but what about the one-arm routing mentioned in Project 3? It seems like a clever hack for smaller networks that can't afford a massive Layer 3 switch, but does it hold up under heavy traffic?
It's definitely a budget-friendly solution, but you're literally forcing all inter-VLAN traffic through a single physical cable. It's like having a 4-lane highway merge into a single-lane bridge just across a river. It works, but you'll definitely see some congestion during peak hours.
And that bridge relies heavily on sub-interfaces and 802.1q tagging. If you forget to enable RP broadcast on those sub-interfaces, the router can't actually communicate with the hosts in the VLAN, and you're left wondering why your pings are failing despite the ports being up.
That's a classic troubleshooting trap. It's similar to the RP issues we see in VRRP, where the virtual MAC address needs to be correctly mapped so that the traffic knows which physical box is currently acting as the active gateway.
Speaking of troubleshooting, the syllabus emphasizes the /tracert command. I used to think it was just for checking if a site was down, but in a multi-hop enterprise network, it's the only way to see if your floating route backup path is actually taking over when it should.
Exactly. It's the X-ray of the networking world. If you see a packet hitting a router it shouldn't, or dying at a specific hop, you immediately know if your static route has the wrong next hop IP, or if an ACL is silently dropping the traffic.
I noticed the syllabus ends with comprehensive training. It feels like that's where all these pieces, DHCP, OSPF, NAT, and VLANs, finally collide. Do you think the biggest challenge for students is the configuration syntax or the actual design of the IP address plan?
The syntax can be Googled, but a bad IP plan will haunt you forever. If you don't leave enough space for subnet growth, or if your address ranges overlap, no amount of OSPF magic will fix the routing conflicts that follow.
That's why subnetting is listed under memorization and proficiency. You have to be able to slice up a /24 block in your head to ensure the marketing department and the server room don't end up fighting over the same gateway address.
It all comes back to a solid foundation. Once you master the boring stuff like subnetting and port types, the exciting stuff like building a high-availability campus network becomes much more intuitive.
If we look at the assessment objectives for Project 2, there's a heavy focus on VLAN frame formats and port types. Why does the exam care so much about whether a port is, access, or trunk, when a packet is just a packet?
Because that's the most common source of network failure. An exam question might ask what happens to a tagged frame hitting an access port. If you don't know the port will strip the tag or drop the frame entirely, you can't troubleshoot why two departments can't communicate.
Right. And then there's the trunk port logic. The exam usually tests if you understand that a trunk can carry multiple VLANs, but it still needs a native VLAN or PVID. If the PVIDs don't match on both ends of a link, you end up with traffic leaking into the wrong department.
Exactly. Another big exam point is the difference between Layer 2 and Layer 3 switches. A classic question asks how a Layer 3 switch handles the first packet of a flow versus subsequent packets. It routes once, switches many, using the hardware-based FIB table.
That's a huge performance gain over traditional routers. Moving to Project 3, the syllabus highlights floating static routes. I bet they love asking about administrative distance, AD, and how to manually set a priority to ensure the backup link stays dormant.
They definitely do. You'll likely see a scenario where you have two paths, and must choose the one with the higher preference value to be the backup. In the VRP system, you have to remember that a higher times numerical value actually means a lower times priority.
That's a trap many fall into. What about OSPF areas? The exam requirements specifically mention Area 0 and non-backbone areas. They probably want us to identify which router acts as the area border router, ABR, to summarize routes between them.
Spot on. You'll be asked to configure an OSPF process and assign interfaces to specific areas. If you put an interface in the wrong area, the adjacency won't form, and the routing table will stay empty. A perfect setup for a troubleshoot and fix exam question.
Finally, don't forget NAT and ACLs. The exam often tests the match order. If you put a permit all rule at the top of your ACL, your specific security blocks further down will never be reached, leaving the network wide open.
It's all about the sequence. Whether it's the order of an ACL or the priority of a VRRP master, the exam is testing if you understand the decision-making process of the hardware, not just the commands themselves.
Looking at the assessment requirements for Project 2 again, I noticed they specifically mention STP and RSTP. In an exam scenario, they love to give you a diagram with 3 switches and ask you to identify which port becomes the blocked port to break the loop.
Exactly, and to solve that, you have to follow the election logic. First, find the route bridge with the lowest priority, then calculate the route path cost. It's a classic step-by-step process that testers use to see if you actually understand how switches talk to each other.
I've seen questions where they change the priority of a switch to 0 just to force it to be the route. If you don't catch that detail, your entire map of designated and route ports will be wrong, and you'll fail the connectivity question.
It's a high-stakes game of follow the logic. Speaking of logic, let's talk about the DHCP troubleshooting on the exam. They might show a client that has an IP like 169.254.x.x. Do you think students realize that means the DHCP request never reached the server?
That's a gimme point if you recognize API, but the harder question is asterisk why it failed. Was it a missing DHCP select global command on the interface, or was the VLAN interface simply down? The exam tests your ability to trace the path of that DORA process.
DORA is the heartbeat of the access layer. Now, shifting to Project 3, the RIPv2 versus OSPF comparison is a staple. A favorite exam trick is asking about auto summary in RIPv2. If it's on, your subnetted routes get bunched back into a single classful block,
which completely breaks your specific IP planning. It's interesting how the syllabus stresses RIPv2 specifically because it supports VLSM, yet one wrong command like summary can negate all that hard work in a medium-sized campus network.
And then there's the OSPF hello timer. If the timers don't match between two routers, they'll never become neighbors. I've seen exam questions where the configuration looks perfect, but the link is dead because one side is set to 10 seconds and the other to 30.
It's those invisible mismatches that define the comprehension level of the assessment. Even with NAT, they might ask you to distinguish between static NAT for a web server and NAPT for general office users to see if you understand port-level multiplexing.
That's the ultimate test of resource management. If you can explain why NAPT allows hundreds of users to share one public IP by tracking their unique port numbers, you've basically mastered the core of modern WAN access.